Let's take function sine of x. Now, can you transform sine of x so that our new function only intersects sine of x once, while still being bounded from both above and below? Well, at first it may seem impossible. The sine function repeats in an infinite interval. Whatever function we make will surely intercept it again. To find an answer to the question, we just need to understand how the sine function works. So let's take sine of theta. If we draw a circle, we can create an angle on the inside. The value of this angle is theta. Theta is our input. The length of this green line is our output. Now, you may wonder, what unit is theta? Well, theta is in a unit known as a radian. A radian is the length of our radius on the circumference of a circle. Now, you can convert radius to circumference by multiplying it by 2 pi. You do the same for radians. There are 2 pi radians in the 360 degrees of a circle. And so, with the basics covered, we can get to graphing this function. As you can see, as our theta value increases, our output value creates a sine wave. Let's extend this sine graph to a larger graph so we can find a solution to the problem we posed earlier. Recall that one full circle consists of 2 pi radians. With that said, it makes sense our wave repeats in intervals of 2 pi. So, for step 1, we need to find a way to make our new function. We can multiply our x value by the irrational constant pi to make our waves repeat in intervals of 2 rather than 2 pi. We can then add 2 to place our new function right above our sine function, and then we can shift it a little to the right, and now we have an intercept point right at x equals pi over 2 and y equals 1. And our new function even lies between the range 1 and 3. And no matter how far we go, it will never intercept again. It may get close, such as around x equals 90. However, if we zoom in, you can see it doesn't quite intercept. Now the question is, why does this solution work? Well, recall sine of x repeats in intervals of 2 pi. Why is this important? Well, let's take a random decimal point value, say 2.7. What value do you need to multiply this number by for the output number to have this exact same decimal value? If you said 11, that is correct. Now how about 2.71? Well, you need to multiply it by 101. And now for 2.718, we would need to multiply it by 1000. We can write a formula to find the value we need to multiply by a decimal value to get the exact same decimal value. Our own function looks like this, where function of n equals 10 to the nth power plus 1. For example, let's take 1.5578. There are 4 decimal places in this number, so we replace n with 4 and do the math. And the value we need to multiply this number by is 10,001. How's this connected to the 2 pi intervals? Well, each time the wave repeats, you're multiplying by 2 pi. What value can you multiply pi by in order for it to have the exact same decimal value? Well, if we plug it into our formula, it doesn't work. Pi is an irrational number, it has an infinite number of decimal spots. If we plug it into the formula, we would be inputting infinity, which wouldn't work. Whatever value we multiply pi by, it will never have the same decimal value. Our new function, however, repeats in intervals of 2. 2 is a whole number, so no matter how far you are on the graph, the peaks and dips will have the exact same decimal value as they did when it intercepted sine of x, whereas sine of x won't have the same decimal value, so they will never intercept again.